Hello all, so this is team number 15. Myself, I'm Nishant Sachdeva and my teammate Sarthak Mahajan are sitting in this meeting and we'll conduct the demo for our project, the distributed web crawler. So our project works on two parts. One is the handler from which we give inputs and the other are the client or the nodes. As far as our implementation is concerned, our nodes work with Flask and our handler works on Python. Now, before going into the details of how the project works, I will give a demo and show how it's working. Thereafter, I shall go into the theoretical portions of the code. A few things to start off with. We assume there's absolutely no node failure. We assume that the commands are not going to be contradictory. They're not going to be any edge cases. And we assume that there are 4 client nodes available. Now, about this last assumption, the 4 client nodes are an arbitrary number. It can be any number of client nodes, but it has to be specified before. All these nodes are initialized before we begin our code. So now I'll start my demo and I hope there are no issues. If there are any, I'll address them after the demo. So as you see, my first node is active. So what we notice here is that the port number for every port has to be given as an argument to the command. Right now, I have broken my terminal using tmux command. So as we see now, all my nodes are active. All my Flask nodes are active. These are the ones which actually make my distributed system. Now, as for the crawler, there are 4 types of commands that go into the crawler. One is the actual crawl command where we say, okay, crawl a given website up to a certain number of levels. The other command is the making of the graph. So what is a graph? Basically, you give a website or you give a URL. You demand the depth of the tree that would result as a result of crawling, and you say, okay, display that graph. The third command that we have is the showing of HTML. So obviously, if we are crawling, we need to have some sort of evidence of where the HTML is being stored. And the fourth is obviously the quit command. So when you say end, my main.py file ends. So my P3 by the way is just an alias. It says Python 3 actually. So this is main.py. These are the 3 URLs that are active right now, where from which it will interact. So remember this localhost is being used because we're only targeting proof of concept here. Otherwise, all these nodes could easily be on different systems. So my first command is going to be crawl. And for testing crawl, I can have any website. It really doesn't matter. Let's start with a usual google.com search. So what happens with this is I'll enter my website here. It will say, okay, how many levels? Okay, so right now I'll go with say maybe 3 levels. That's pretty standard. I'll run the command. And as you see, all the nodes are active right now and they're crawling. And they have divided the work amongst themselves and now they're crawling. So once the crawling is over, I'll get a message on my main.py file which will say, okay, crawling is done. By the way, you have to also know that each of these clients has storage which is completely independent of each other. It has absolutely no link with each other. So now crawling has returned with an OK command. I will give another crawl just for the sake of it so that we have more data to actually test on. So this time I will enter, let's say, Triple IT Hyderabad website. It's not a big deal. We're just trying things out here. Okay, so yeah, so we'll just give it here and let's say, let's go this time, let's go a bit deeper. So let's go 4 levels. There's no restriction as such, but we want to keep in mind the RAM constraints of our own system. So that way we'll not go very high, but let's try with 4 levels. So it's not a big deal. They work as usual. The exact working of this, I'll go into it once we're done with the coding parts. So this is just crawling right now. It's 4 levels, so it will take some time, but it's all distributed. It's giving work to each other. The exact architecture, I'll get into the details of it once the demo is over. But they're all message passing right now. They're all talking amongst themselves, but there's no shared memory. There's absolutely no concept of shared memory. They all have their own memory, and they only talk to each other when they need to pass messages. Message passing is the only medium of communication these nodes have with each other. The 4 nodes and the main.py file. Okay, so that crawling is done now. So now what I'll do is I will run the command make graph. I have done 2 crawlings right now, so I don't see any reason of extending it further, but okay, let's run make graph. Let's also run this on the Triple IT website. Now it asks for depth. So depth, what really it means is that okay, we crawled till the level 4. We can have any depth till 4, if not beyond or earlier, either way it will work. The code does not crash on any of the cases. So I'll just say, okay, let's do 2. So you see how the distributed system is working and compiling the graph here, and the output will be displayed once the process is over. We have to know that sometimes it can take very long because as we saw, the triple IT was grounded till the level of 4. So crawled till the level of 4. So there's a lot of data that it has to go through. Especially on a website as big as triple IT. So there's a lot of subsidiary links that can form a graph. Okay, so the process is over. Now, I agree. There's a caveat to be looked at here. The graph, we have not made an actual graph. That's something we could not do because of time constraints. But what we have displayed here is edges. So what happens is this is node 1, and this after a comma we have the node 2. So this way we have the list of all the edges that will form the primary graph of depth 2. We could also have a graph of depth 1 or a graph of depth 3 as we saw. All of that is possible. Now, for the last command of the demo, we have what we'll call show HTML. For this, we'll just do the Google command because Triple IT, as we saw, could possibly end up taking more time. It has a lot more links. So this is show HTML, and the website we want to go is google.com. So what it will do is it will just display the usual HTML. There's nothing very special in that. It's just the normal HTML. But what we notice is that the HTML is actually stored in the hard disk. The graphs, the non-persistent data is stored in the RAM itself, but the graphs actually go in the hard disk. So this finishes our demo. Now we'll just use the end command. The code also is pretty good in the way that if we enter any random command, it will actually throw an error and ask us to try again. We have the end command, it will simply end the demo. So this way we've seen that, okay, everything has ended. Our nodes have worked perfectly fine and entirely to our satisfaction. They have not given any error and they have not deadlocked. And now we will actually get into the theory of the whole thing. So let's take a proper look at how everything works. Our primary file, as we saw, was the node file and the main.py file. We'll go into them one by one. So first we'll start with the main file. Now main file, like we said in the starting, the number of ports are hard for them, they are fixed. But if we want to change them, all it takes is 5. So we can change them here. There's no big deal in that way. We make the URLs based on the number of ports. And once we do that, we have an infinite loop where a command is entered. And then depending on the command, we remember seeing 4 different commands. We have 4 different processes that take place here. The primary function of the crawler, which is scroll, is the scroll command. It enters the website, it enters the levels. What happens is it picks up any random URL out of all the URLs and it starts from the crawling. The first website is sent to the any random URL. What happens after that? We expect the answer with us. This is the request.get. This is where the actual crawling happens, and then we get our answer back. If there's any error, we say, okay, crawling operation did not complete. Now let's study the crawling process. So what happens when we call the crawl command? We saw that we took any random URL to start with. This node file is the same code for all the Flask workers. The code is completely independent of each other and they all have independent storage. What happens in the crawl command basically is, so we say, okay, first give us the website, then give us the levels that have to be crawled. If the level is bigger than 0, so what we notice is that the calls will be recursive. So if the level ever goes equals to 0, then we don't need to crawl anymore. So we say, okay, crawl. This crawl function it gets imported from another file altogether. We will see that later. Now, if we say, okay, this crawl function returns the child URLs. And this limiter is basically what we use because of the space constraints. There's no need to actually limit the number of children that a URL has, but for our purposes, we put the limit so that we only have a few kids to deal with. That way, our RAM does not get exceeded and we can actually run the code seamlessly. Then for every child, you assign it a new node by using the same random URL function. So once you're on the node, you get the children from that node, and then you send the children nodes to any random node. So that way it's purely distributed. There is no repeated calculation happening in a particular node. Every node does its work and assigns the rest of the work to other nodes. So that way, once we have decided which node to assign it to by completely random processes, we create the request function and then we send the function. After that, what we do is we we assign it, we store that thing in its local storage. So we store the child nodes and we store the outputs that we got in the local storage. How this local storage is used, we'll find that out when we're trying to make the actual graph for the function. Speaking of the actual graph, we come to the main.py file where the actual graph command is called. So the graph command is called, and what happens here is that, so when we send the graph make graph command to the actual make graph function or to any of the node, what it does, it accumulates the adjacency lists through completely distributed mechanisms. It runs basically sort of a DFS. So what happens in a DFS, it calls a node, it figures out if our current website is there in that node or not. If it's there, it contacts all of its children. Then one by one, it picks up the children. So what happens with in that? So when we were crawling, we had sent the children each to different nodes and we had recorded that. So now when we are on a particular website, we know where all of its children have been crawled. So one by one, we in the form of DFS collect information from for every child from different nodes through message passing. Once that is done, we compile the information in our main file here. We compile that information in our main file here. And then we remove all the non-unique elements. Now we have to know that since we are on different systems, they could actually be repetitions for the same website. So we remove all the repetition and then we make the final graph. Now the final graph could not be made in GUI form, so we made an edge list for it, which is practically equal to the actual graph. Now we mentioned how we will see the crawler function at some later. So the time has come for that now. So how does crawling happen? It's pretty simple. It's actually very simple. The crawling part is actually very simple. So we just simply send the request, we convert that to text, and then we use the beautiful soup library with the HTML parser to figure out all the A tags. A is the actual tag where the hyperlinks are stored, the new links are stored. So that is the HRV. Now, once we have the plain text from any particular link, we store it in the HTML using the hard disk. Then we have a storage folder for the same purposes, and we remove all the slashes because that if we don't, then the Ubuntu or any other operating system will confuse them for path labels, which should not happen. So we replace them with nothing, and we store them as .txt files. So when we want to see the txt files, we say use the command show HTML. We enter the website. We run the same process of name generation, and then we read that name from our folders. These type of three functions are run on our system. This here now reduces the demo. This here now reduces our work into three functions, and our demo concludes here. We thank you for putting up with us. We thank you for the patience. We thank ma'am for the extensions she allowed us. Our team was in huge trouble. Two of our members got corona and one member had to fall out of contact because of certain emergencies. And we really thank for the patience and really appreciate all the help that has been given. Thank you. We'll conclude the demo now.